Okay, so let's see what happens if you apply a general Runge-Kutta method. It's like to a system of linear differential equations. So if you apply sort of RK to basically y prime is a of y, right? You have yn plus 1 is equal to yn plus h sum from I equals to 1 to s of bi a yi, and then yi is equal to yn plus h times the sum from j equals to 1 to s of aij yj, sorry. Okay, and then you can expand yn plus 1 and the yi's in an eigenbasis for the matrix A. Okay, so for simplicity, I want to write the eigenvectors as columns of a matrix U, and then you let lambda be the diagonal matrix of eigenvalues. Okay, then the eigenvector relationship can be written as A acting on this matrix of eigenvectors is equal to lambda times, well, actually U times lambda, where U is the matrix of eigenvectors as before, and then lambda is the diagonal matrix of eigenvalues. Okay, so what that basically means then is that U transpose AU is equal to this diagonal matrix of eigenvalues, right? So you can have a diagonalization that's like of the matrix A, and then you can define new vectors. It's like instead of the y's, it's like introduce new vectors z, which are sort of transformed versions, if you will, of the original vectors. So I define let's see, Zn and Zi as follows, that Yn is U Zn, and then Yi is U big Zi. Okay, then it's like in this sort of transformed coordinates, you get the following. Then you just have that U Zn plus 1 is equal to U Zn plus h times the sum of bi au zi, I equals to 1 to s, and then U, alright, so actually let me just simplify this a little bit more. Okay, so this is equal to U Zn plus h sum I equals to 1 to s of bi okay, so U times Z is equal to lambda times Z. Okay, because I have A times U, right? And A times U is U times lambda. All right, so I've factored out U on the left, and I'm just have lambda times Ci. All right, so this implies that Zn plus 1 is Zn plus h, the sum from I equals to 1 to s of bi lambda Ci. Okay, and you can also check that Z super I is equal to Zn plus h sum from j equals 1 to s of aij lambda zj. Okay. And then since lambda is diagonal, this decouples into a system of independent iterations. Okay, so since lambda is diagonal, right, we get independent iterations. And so it is sufficient for stability to consider basically what happens if you were to apply the Runge-Kutta method instead to a system of linear differential equations, to just a scalar linear differential equation. Of the RK method. To a sort of scalar differential equation, right? So just dy dt is equal to lambda times y. And then the only thing, of course, is that the lambdas come from the eigenvalues of the matrix A, so you need to look for all lambdas which are in the spectrum of A, right? Where lambda is in the spectrum of the matrix A. Okay, so just don't be confused. This is the matrix A, which defines the linear system of equations. It's not the matrix A, which is the Aij coefficients in the Runge-Kutta method. Okay, so in any case, what that more or less says is that instead of studying the stability theory, it's like for when applied to a system of linear differential equations, all that's really sufficient is for you to study the Runge-Kutta method applied to a linear sort of scalar differential equation, but where the lambdas are in the spectrum, it's like of the matrix A, of the original system, linear system. Okay, and then the corollary of this is that given a linear sort of system of differential equations, okay, y prime is equal to ay, right, with a diagonalizable matrix A, right? A given RK method with stability function R, right? Then the origin is stable. For the RK method, applied to this system, y prime is equal to ay, if and only if, right, the stability function R applied to h times lambda has modulus less than or equal to 1, okay, where lambda is in the spectrum of the matrix A. Okay, all right. So that tells you something about stability of Runge-Kutta methods, how they're related to this idea of stability functions, and how you can use this model scalar linear differential equation, it's like to say something about stability.